Okay, so let's talk about resistors in series and parallel. Here's an analogy that might help because a lot of people have good intuition for resistors in series. If you have something difficult to go through and then another difficult to go through thing in series, one right after the other, it makes sense that it adds the resistances together. It makes it, if they're equal resistances, twice as hard. But the idea of parallel resistors is often counterintuitive. If we add resistors in parallel, the total resistance of a circuit goes down. How the heck is that possible? So here's the analogy. Imagine it is 3 days before Christmas, and you are going to your favorite big box store to do some shopping. You pick up your stuff and you're ready to go to the checkout. The checkout lane acts as a resistor to the flow of people out of the store. So people are kind of like charges, the people who want to go out of the store, but there's a resistance to the flow of people. All the people have to go through the checkout lane. So the checkout lane is like a resistor to the flow of people. If you only have one checkout lane 3 days before Christmas, what's going to happen to the flow of people out the door? It's going to be very small. So what do? You call and say, we need more checkouts open. And you open another checkout lane. What happens to the flow of people when there are two parallel checkout lanes running? Well, you get more people out the door. There's a bigger flow of people. And every time you add another checkout lane in parallel, where the people or the charges can go through this one or this one or this one or this one, then what you end up with is a larger amount of people flowing out of the store. You end up with a larger current flowing through the total circuit. And so that's an analogy that sometimes helps people figure out how parallel resistors can actually reduce the total resistance when each resistor makes life harder for charge to flow through. And it actually, the analogy works as well for the flow of people. If you think about airlines and airports, if you've ever flown, then you know that, okay, you get to the airport and first you have to go through a checkpoint where they check your boarding pass and your ID. Okay, that is a resistor to the flow of people trying to get to their gate. Then after you go through that check, you have to get stopped again where you have to dump all your bags and maybe your shoes onto the scanner, the belt, and you have to go through and get your bags checked. That is another resistor to the flow of people. But in this case, those two resistors are in series. You have to go through one and then through the other. So what happens to the total amount of people flow? How many people flow out of that checkpoint per minute? Well, it goes way down. If you only had one of those two to deal with, you'd have more people going through. You'd have more charge flowing. But because you have two resistors in series, one right after the other, then what happens is the total amount of people or charge flowing per second, per minute, whatever, is reduced because, okay, I've got to go through this thing that slows me down. And then I've got to go through this thing that slows me down. Versus in parallel, where you have options. And so all this big line of people behind you trying to check out of your favorite big box store, they're all saying, okay, if there's one checkout, everybody has to go through that. But if there are 10 checkouts, we can all spread out and the amount of flow is greater. So there's an analogy that I hope helps you make sense of resistors in series and parallel.